Well, you will remember that we had said that here the pharmacophore was two nitrogen atoms at a certain distance from each other, and that distance is around, it could be less. But for example, it serves with 10 carbon atoms, and these were affinity ligands to the nicotinic channel receptor channel, and that we had already seen there on the side is the molecule of chameleon, and as you can see, it is simply two 100% positive nitrogens at a certain distance. Clearly, this is not necessarily the conformation that adopts within the nicotinic channel. The conformation that a molecule adopts within the receptor is not necessarily the conformation in the void, or not even in water, but there is movement. There are conformational changes. Well, next example. Then these pharmacophores, I want you to remember, because let's see. First, it is impossible for reasons of time that we see that exist in literature, and always new ones are discovered. What I am showing you here is a pulp that gives rise to many things. Then they were not chosen randomly, but many of these pharmacophores open the doors for several other therapeutic relevant systems. Notice the following. I want you to first see this. What is down here asks what is adrenaline and noradrenaline, and which is the neurotransmitter. Which of the 12 neurotransmitters? Very well. This is neurotransmitter, and this other is hormone. The only difference between both is that one has a methyl group and the other lacks. That methyl group, metabolically, you can obtain noradrenaline from adrenaline by a metabolic reaction called methylation. Then another metabolic reaction that can give rise to products of interest is the methylation N. To cut a methyl group of a nitrogen, or even sometimes a small chain, this occurs at the hepatic level, that is at the level of hepatic cytochromes, cytochrome 4, 150, some variant. Well, what can you tell me in terms of the degree of ionization of these compounds? APA7 will be neutral or ionic perfect. They will be 100% ionic APA7 with positive charge. Both will be positive AA7 second. What can you tell me about the chirality of the chiral spiral carbon? What configuration does it have, R or SE? Very well already. Perfect it is, of absolute configuration. R, that is the automer that is responsible for the activity. If the configuration is reversed, there is no adequate bioactivity. It does not link properly to the adrenaline receptors. Well, we are now, having seen these structures, to see something very interesting. This plant that is here is Ephedra vulgaris, and from the leaves of this plant of Ephedra vulgaris, it is extracted. As the name says, ephedrine, you notice the tremendous similarity of this that comes from a plant with adrenaline and non-adrenaline. It is noticeable. The only difference is that one, we do not have catecholic hydroxyls, and two, there is an additional alkylation in the chain. Then, based on the fact, chemical structure, that you believe this can or cannot go through the hematoencephalic blood-brain barrier, very well, it is quite lipophilic. It has greater lipophilia, greater the P, than the non-adrenaline or than the adrenaline. And because it has greater lipophilia, because with the hydroxyl groups there is a direct correlation between Pegasus and lipophilia. No, be careful, they are not. The same Pegasus A is not the same as lipophilia, and there is no direct correlation, not because something is protonable means that it is not lipophilic, or vice versa. They are different concepts, well imitating. This molecule, it turns out that ephedrine is a powerful nasal vasoconstrictor. It is a powerful brain stimulant, and it is also a compound that suppresses appetite well. It is so that, by simplification, this synthetic molecule called amphetamine arrives. Ask, what does this curve link mean? Very well, that is the racemic mixture that we can have our configuration, or that indistinctly is not so relevant for activity, that is one or another, in this case, in specific question, and this is more or less lipophilic, then more very well because it has or lacks the hydroxyl of the chain of ethanolamine, so it has even greater input to the central nervous system, even greater the P. This molecule then, with this type of pharmacophore, you are going to see a lot. And when they find aryl, that is, aromatic systems of type ethanolamine, you immediately suspect that that is going to have brain activity. Phenyl systems, ethanolamine, or aryl oxypropanolamine, that is, a benzene in a short chain with a nitrogen, tend to have activity in some target at the brain level. Yes, I think I have it here in the one that follows. Look here. There was only one, so that you can see how this synthesis and this part of the story is very easy to obtain by condensation. We can obtain how this functional group is called. This is not an amine. What is the generic name of that? And it starts with perfect, and amine. It is important to know the difference, because we are going to see that there are drugs. Example, in some antibiotics, there are amines, and it does not give the same configuration of the amine with the configuration of the amines. What happens if the amine is substituted? Would happen, this is hypothetical already, that if this amine had, for example, it has an electronic pair, it would be, as it is there, E or Z. It is not the same, it is not true that is. It is not the same that this red methyl group is on the top, right? Or that it is on the left. There is no book rotation. The amines then have geometric isomerism. As it is here, it would, because we have that the groups of greater priority that are the methyl, and here the chain is on the top. Opposite to Z's, be careful not to confuse that Z, because two methyls are seen on the same. You have to see by atomic weight and zip rules of assignment of priorities, so that I leave them there. As data, the amines can generate geometric isomerism, and therefore we can have two drugs from an amine well, and then by reduction, it is simply shown reduction, you cannot obtain the mixture. That is, the amphetamines. That is why molecule. Now one understands why they are controlled. You cannot arrive, and by that, in the market, they are going to ask for a card, a certification of the ISP, that is for in a home laboratory, is obtaining amphetamines. And so that is why there are certain products and why that is controlled well. There is the chemical reason for what it can end up becoming, and it is not that the amphetamine itself is bad. If they look, they are, that is, they raise the mood and suppress the appetite. The problem is the drugs. Drugs, for example, to have more performance in a competition, drugs that the criminals consume when they go out to assault, that is the problem. But there are that have been used in suppressor supplements of the controlled sale appetite, is called that. There, I do not have the structure here. And when one speaks of pseudoephedrine, I thought I had it here. Is when we have the mixture of diastereoisomers in this position. Okay, here I have only one enantiomer. But when I have a mixture of diastereoisomers that, well, It says here, other ways of discovery. It is very rare from secondary mammalian metabolites. Because the amount of animals that would have to be sacrificed is very high by imitation. Or vitamins by extraction of natural sources, for example, antibiotics today. New antibiotics are discovered from the marine background, particularly bromate molecules in marine metabolism. There are bromate alkaloids, and that is rare because we know that, for example, the proteins had bromine, no, but at sea level. There are some mollusks or marine plants that can produce bromate alkaloids, sometimes accidentally discovered things that one does not test in the laboratory, or there is an unexpected effect of a well-known drug example. And exactly, it is a typical case, and the sildenafil. What was the first application, or for what it was being studied to combat the respiratory insufficiency? That is, it was a powerful bronchial vasodilator. It had beneficial effect at the respiratory level. Then the first application was at the level of the respiratory system. But then it was found that it was also a peripheral vasodilator. Another example, and that is why it serves for erectile dysfunction, because it is peripheral vasodilator for the release of nitric oxide. And on the other hand, another example, as of the last decades, is what happened with fluoxetine. The fluoxetine is an antidepressant. And that was the isoniazid. That is also close. If the isoniazid was also for tuberculosis, then it was discovered that it was antidepressant. Is antidepressant. Okay, it is. But it has also been discovered several things, for example. And also, now last, it was discovered that it was antiviral, that is the rare. Always then, a new application is being discovered of a drug already for sale. It will be convenient, that of course, yes, because you have to invest less in adverse tests in animals and in humans. Look here, I have an accidental discovery, as it is that psychotropic were discovered. Call it Claudius epoxy or any other psychotropic, such as alprazolam, diazepam, clonazepam, etc. We have to, instead of discarding this molecule that they obtained when testing, it was found biological effect, in this case of GABAergic type, then what they expected was this type of cyclation. And I could ask them what type of cyclation is, and why it is not happening. Okay, Yusuf, what kind of cyclization? Reaction is this 1, 2, 3, 4, 5, 6, 7. The type of according to Baldwin rules. Seven I say. A type 7 cyclation, that is, we have that a cycle of 7 will be formed exo because an electronic pair goes out of the system, and trig because the attack is taking place in the sp2 carbon. That we have there, that is a way to classify cyclations, and it turns out that not all cyclations are favored. A problem here for the cyclation is what we were just talking about. The imini, this imini is E or Z, as it is drawn there. So now you start to think already. Okay, we have, that is an electronic pair, like the substitutes a priority, one which would be oxygen, and here I have to discriminate between carbon or carbon, yes, and nitrogen, and this is close to nothing. Then priority, one for here, then it is, and it is already a configuration imine, and it will be comfortable to attack with the hydroxyl, looking at the opposite side. No, okay, if it was Z, with the hydroxyl up, obviously, that entropically it is more favorable. Well then, it does not happen. It says it happened. What is down here? Okay, this cyclation occurred. Difference between this system and the one above the system that is up there is not aromatic. But the system that is down here is 100% aromatic. Then it is more stable, and therefore it was more favorable that it was generated. What happened here? Who actually attacked perfect then? What happened was the nitrogen attack on the carbonylic that attack. If it was favorably entropically a cyclation of 6,6-exotric, the nitrogen was the one who attacked. And we have this new system. And now this is called that it has two nitrogen atoms first. What is called this type of functional group. That the neutral load, the net load is 0. But this has a name. This group appears in E. Several pharmacies, and well, the same chlorhexepoxy, because it is here. It has it at the end. And what is called that type of group is called N-oxide. And what is called the hetero, because it is a heterocyclic with two aromatic nitrogens, 100% pyridine or pyrimidine, or pyrimidine. Then we have that it is pyrimidine aromatic system. And the second step in this obtaining something that could serve for the nervous system, we have the following reaction occurs. Here it says it does not happen, and below it does happen. What is this methyl mean? A nucleophile. Therefore, there will be a nucleophilic. And there it says, for example, above it, says it does not happen because the R allows me to mark it. Presents an electrophilic carbon. Then I am going to mark here what we have there as R. It says GTL. Then the above that does not happen is this attack that did not happen. This attack with loss of chlorine. Interestingly, a simple SN2 type reaction does not happen. But if the expansion of the system occurs, that is, who was actually attacked? The carbon was already very well attacked. That's right. We can see that the portion here at the end, the nitrogen with the methyl group, is connected to this carbon. That is, to this carbon here, and a expansion reorganization occurs. That is, what happened was the following first. Carbon is exactly brutally electrodeficient, both due to the effect of pyrimidine nitrogen, as well as by the N-oxide, and to a greater extent by the N-oxide. Then, that carbon is so that it acted as a carbon dioxide. It has a strong positive charge differential and experienced an attack with reorganization. The system opens, and at the same time, the system later, this captures the electronic pair, attack this one here with the expulsion of chlorine and the expansion of the system that we see down here, and we have a benzene. Diazepine, very well. That is the generic name. The official name is chlorine diazepoxy. We have a benzodiazepine. We have a benzodiazepine of short action. The chlorine diazepoxy, they to this day in pharmacies to induce sleep. Because it is of short action, person cannot conciliate the dream all night. They give him something of more long degradation time, so that the effect lasts all night. But this is of sleep, with controlled sale, of course, and many people use this to get drunk and to sleep for weeks. And then that would be the accidental discovery of benzodiazepines. Interesting, already interesting, how accidentally we can get to compounds of therapeutic interest. Let's see another case here. It says unexpected effect in the therapeutic application of known drugs. To see this image that is down here is familiar to you. It is not true. It is very good. It is a nephron. It is the minimum structural unit of the kidney. And what happens in the nephron occurs the filtration and then the creation of the urine. If here metabolites are reabsorbed and the waste is excreted and through this collector tube, the urine is formed. Well, in several parts of that nephron there, diuretics can act. That is, molecules that favor the elimination of water and electrolytes through urine. An example, says there, the hydrochlorothiazide, which is a diuretic that comes from the chlorothiazide. TAT has a poor diuretic effect. The only reduction of this link increases the diuretic effect, because it turns out that the molecule can be better accommodated. Because to see how this simple change makes the final compound can be better accommodated in the gene. Target. It is very simple which of the two loses rigidity. In this case, we have that the final compound is less rigid. That is, the chlorothiazide and the hydrochlorothiazide is better accommodated. Second observation, in the first case, a hydrogen bridge donor. Instead, here we have two hydrogen bridge donors relevant for the interaction with the target protein. Well, this the hydrochlorothiazide, thus being synthesized to generate an antibacterial drug, ended up being diuretic. See? Starting antibacterial is a sulfonamide. That is, whenever you see the sulfonamide group connected to an aromatic ring, you say that it will be antibacterial, because it imitates what cofactor the bacteria occupies, and we saw it in the last class to see this imitates this fragment. Acid for benzoic amino, OK, imitated the pava, which in turn was a brick to synthesize folic acid. Now they are remembering a little what we have seen, and it is important that they integrate all those molecules. They have to retain those pharmacophores in their mind. Well, let's go to the next one. Says here, discovery, based on a biochemical strategy here. I have two examples on the lie, because there is a lot of this in reality. But let's see the first case. The first case we have to the right we see. First there to the right, we have dopamine. Good dopamine. First, what is dopamine? Very well, it can act as a neurotransmitter, and it has been seen that it can also act as a hormone because it can travel through the bloodstream and reach, for example, the kidneys to various parts. Then it has a dual behavior. Now, dopamine as a neurotransmitter in the brain. When it is scarce, it gives rise to the diseases of very well Parkinson. And in fact, it does not tell us there. But a decrease in the concentration of dopamine implies Parkinson. Then many times more. Then because the same dopamine decreases, one of the problems in Parkinson is that dopamine receptors are destroyed in the brain. Good, because then one says, well, as compensation, we give more dopamine to the person. Problem, we cannot directly administer dopamine as a drug because this type of structure already very well. It is very difficult to cross the encephalic barrier. And apart from that, it is extensively metabolized at the hepatic level. Then we have two problems. This they do not have to know, but the hydroxylo that is most metaproduction, and that implies that the molecule is not going to reach practically nothing. Brain, while there on the right, you will not know the following. Here on the right, we have this other molecule that is called the EDOPA, that as it has technically what it is, a carbohydrate, or an amino acid. I heard a carboacid, an amino acid. Artificial, it says, a dopa, okay, L. What did this mean of L? We saw it. Because it is the one that I sent to the polarized light, and it is from the feature series. The D to the right, and the L to the left in the conventional feature projection. Very well. Then this is from the feature series. And do not forget that they mean that type of little things. Well, we have that this in itself is a precursor of dopamine, and as it is an amino acid, it reaches the brain easily, and you will say, but how, if it is super positive? In fact, structures with charge receives the name when the net load is zero, receives the name of Sweiter. That I also think that we had already delivered that concept, and one says, but if the dopamine does not enter less to enter this, is that there is a difference, and it is that the dopa administered in high doses is very similar to what amino acid perfect is very similar to tyrosine. New in the encephalic bar, and therefore passes blown through the back into the arteria, transporters of cerebral tyrosine, and reaches the brain in large quantities and inside the brain. What happens inside the brain, I am going to show here. Of course, exactly by action of that dopamine, dopa decarboxylase, that as the decarboxylase or decarboxylase, exact cut here, we have a metabolic reaction that at the level of the laboratory it would be impossible, but see what they are capable of on top piece directly, and therefore asks, and there would be the dopamine. This process was by action of the carboxylase dopa, an oxidation or a reduction. Perfect. It was a reduction. And so, we managed to reach our final dopamine. Very well, down there in the lower part, a cogent is shown, a copharmacist, so to speak, which is not the adopa, but it is an adopa methyl. As you can see here in the car, there is a hydrogen. Now, there is a methyl, and that is co-administered with the adopa. This is not different. It is already another molecule, but the purpose of co-administering this molecule is that that molecule in particular can prevent the hepatic degradation of the adopa, because this inhibits the enzymes that at the hepatic level tend to destroy the adopa, and that protects the adopa so that it reaches the brain. We go to the next case that we have here. Another biochemical strategy, because it is important to know more or less what happens with the molecule inside the body, and we have that in the case of cancer. In the case of cancer, this cycle is overstimulated, the cycle of cellular replication. Okay, and particularly the phase S, which is the phase of DNA synthesis. Then for DNA synthesis, the molecule uses the nitrogen bases. For example, it has to occupy a lot of thymine, and it has to occupy adenine, etc. Well, we can center it only on one, the thymine, is that it is here, the thymine purified base, or pyrimidine. And this thymine base comes in turn chemically by action of the thymidylate enzyme of the uracil, another pyrimidine base. The uracil is part of the DNA or RNA. Very well. Okay, this is RNA. And what the thymidylate does, without cup, to create the necessary thymine adenine, is simply to put this position again. These impossible reactions in laboratory, but here the enzyme does it, and the enzyme can cut, so to speak, this link and place the methyl there. Then what we are going to do, so that the cancer cell cannot create DNA, genetic material, we are going to give it large amounts of something similar to the uracil 5-fluorouracil. How is the size between fluoride and proton? It is very similar, very well. Fluoride and proton are the only two atoms, or rather fluoride is the only atom that is similar in size to the proton. That is why it is placed in fluoride. It does not serve a chlorine, a bromine. Large, it has to be something that looks like the uracil, and the only thing that looks like it is fluor, then 5. Fluorouracil is going to be a competitive inhibitor. Is a competitive inhibitor of what? Of the thymidylate without cup, you will see. But and why the enzyme cannot do the same if fluoride and proton are the same or very similar in size, but very close, because it cannot cut the fluoride and stick the methyl. There is a reason. That what do you think? If it is more electronegative, okay. Eventually, some new interaction with the protein already that adds, without a doubt, some, and there is more still. There is good that you mention it there, because it can do it right. Halogen bridge is with chlorine, bromine, or because it will cost so much to remove the fluoride. If it is so similar to hydrogen in it, technically, there should not be so much problem. The problem is that the carbon-fluor link, the energy of that link is a very high energy. That link is one of the strongest that exists in organic chemistry. I give you a concrete example. We all have a Teflon pan in the house, or a Teflon pot. That is carbon-fluor. The Teflon cover is carbon-fluor. That is, the links are so strong that they resist the heat, you understand me? Then carbon-fluor is not going to be cut. Enzymatic action. Therefore, to the enzyme, it is impossible to remove the and in that way, we get an inhibitor. Good. And here, it says discovery in the present here. We have the two great computer strategies that today are used for the design of pharmacists, and today more than ever with the topic of artificial intelligence. This field is expanding even more, which is all through the visualization of the protein to see the one that exists in these two techniques does not mean that they are excluding one from the other, but that they are complementary. What we are going to is that with a quasar, you build an equation that correlates activity with air, the physical chemical properties, or well, with structural fragments, we have to use physical chemical patterns. They will have to do a statistical analysis, and that gives rise to a new molecule. Example says here, discovery of norfloxacino, quinolone of broad spectrum. Good, this quinolone comes from a prediction made by the quasar equation. That is, the mathematical method called quasar that creates equations. Its greatest value is that it makes empirical predictions. That is, it makes predictions of activity predictions of biological activity, and due to that is that we can synthesize something with more chances of success. And how is this P8 molecule going to be physiological? Very interesting. Loaded where? Let's see. We to be careful, as it is called this heterocyclic, again name of this system, piperacine. Because of course, and which of the two is protonated very well, the secondary is the basic one. This is going to be positive to pH 7. It has a pKa of around 9. On the other hand, we have that the carboxylic acid is superacid, a carboxylic acid that pKa had around 5. But this is less than 5, is around 2. The question is why it is more acid. Careful, what happens is that the load in reality, if we talk about resonance here, the nitrogen, would be increasing the low density, and the carboxylated system is taking away the low density. But that's where the thing goes. That is what makes the acidity of this proton. This link is rotatable. Therefore, this proton is superacid for the following. I will have to erase now to illustrate the point. Since there is free rotation, we have that this can be like this. We are clear that the proton can be there and now if they are going to tell me what happens. And the oxygen makes a bridge, a hydrogen bridge movement. We have there a hydrogen bridges that increases the acidity of said proton. That is why the pKa is around 2. And due to that intramolecular hydrogen bridge that is already taking out the proton of the chemical structure. Then, one of the great utilities of the quasar systems is this, that we can predict the activity that is going to have something new, and to make a quasar equation, it is always a requirement that the requirement is to have the empirical data of IC50. They have to have IC50, experimental IC50. If someone says, I want to make a theoretical quasar with a simulated data, with a calculated data, it cannot be done. They have to have the experimental empirical IC50. If they do not have it, they cannot make a quasar, and I have seen articles even published that they have IC50 predicted by a simulation. That cannot be already by default. Quasar has to occupy an empirical data. Well, in this case, we have the studies based on the receptor. To the first case, to the quasar, the study based on design based on ligand. In the second case, we have based on the receptor. Both are good lives asked to see when, for example, it would be convenient, the quasar. To be careful. And what happens is that to make a quasar study, you need the experimental IC50, and it is not a requirement to know the biological target. When the target is not known here, quasar helps a lot. When the crystallized protein is not available, quasar here helps a lot. But if we have the gene acting on the crystallized protein, and we can see it, there we go to the receptor, okay, and we have the discovery of dorsalamide, which is this molecule that is here, which is a carbon anhydrous. And by inhibiting the carbon anhydrous, the intraocular pressure is reduced because we reduce the formation of, or let's say the rupture of the carbonic acid within the anhydrous humor of the anhydride, reducing the pressure. Because we are generating this gap that is here is an enzymatic inhibitor molecule that comes from docking studies. And what can you tell me about this compound? How many centers does it have? And that one is 1 and the one below is 2. And there is no more. And I do not see another CP3. And what else? How is it going to be loaded already where perfect this is going to be protonated to pH 7? Do not forget that it has a Pegasus A of around 9. What is this teracycle called? And be careful. It is only the 5th cycle. It is not true. It is only the 5th cycle. In fact, this cycle 5 is very special because you know that it could be replaced by benzene. It is because the sulfur is large. Well, this is the thiophene. And the functional group that is here is called this functional group is called. But we have seen it. We have seen it only, that in the case of antibiotics of type blue thanks, sorry, and this sensitive thing moved me a second for. Sulfonamide? Very well. The sulfonamide. And how is it? Because here there is it is not the same. And how? And so we are trying to learn the names of the functional groups, also that always appear. These groups, a little different in medicine chemistry, not only in alkyl carbonyl, or this is already a sulfur, okay, connected to two oxygens, then a sulfonamide. I note, to confuse the sulfonamide, when the sulfur is like this. When it is like this, it is not sulfonamide, and it is another thing. The similar the thiol is when it is a terminal ash with the alcohol. This is called sulfoxide very well. Though they are not the same. Question: which of the two can be chiral sulfonamide or sulfox? We already have divided opinions, and what happens is that the sulfo is good because it has two groups, the same, but the sulfoxide, sorry, could have here a rhone here, a R2, and you say, which is the fourth group? The electronic pair I do not know, then that is why sulfur become chiral. Example, look, we are going to project a molecule. I do not know if we had seen it in the day this, but maybe we mentioned it, but not. We only mentioned it well. Here is the structure of omeprazole that has this heterocyclic that is called benzimidazole very well. And here, pyridine, and here is the sulfoxide. Then this sulfoxide can have two configurations. Here it is drawn in a racemic way. It is not shown where the oxygen is for forward or backward. But look at this omeprazole. It turns out that RNLs do not have the same activity. And where's the starting point for that? It occupies the omeprazole someone has taken. Yes, it is for very well. It is for the gastric ulcer, for uncontrolled gastric acidity, and here we have the esomeprazole. That is the active enantiomer, as we said, to the enantiomer. That is more active, they explain. Here is, it means that the electronic pair goes backwards. The group is H2 comes forward. The most active is called eutomero very well. The esomeprazole is the acetrazole, or eutomero. Of the omeprazole, therefore, it is more expensive. And in fact, if you more clearly, because it is more effective, it is true. Although it is more expensive, it must be 10 times the difference in price. That is, we are talking about that if an omeprazole is worth 1,000 pesos, this is going to be worth 10,000 from there, times the difference in price, because separating enantiomers is expensive. It is not impossible, it is expensive. It is expensive. Well, let's go. Well, and not true. Thanks to all these techniques, then we are going to know how to interact the ligand with the receptor but teacher. And if we do not, well, you create a pseudo-receptor, or well, one with the same cursor, one can speculate around the molecule by extrapolation, as it is the environment, or that one can project the interaction by linking receptors is measurable. It is optimizable, it is visualized, develop a leader. Rationally, I do not know if I think that is only have additional concepts to finish this first part. And here, it is the same but reinforced. With an image, we need molecules for the methods based on linking the cursor. To a large extent, we only need the molecules and the value of IC50, experimental, exactly. While based on a receptor, you need to know the receptor structure that you get from the website. The PD, or protein data bank, obtains the free structure. Obviously, there are not all there. Crystallized proteins then. If just the one you need is not there, you can resort to other method of type cursor. When one part of the protein without anything, that is called the design again. That term again is used a lot in articles. That means from the nothing, that is external, without prior knowledge of a molecule that links to the receptor. And to finish here, I have the great biological targets, and we have that they can be of membrane or cytosol. To see, Christopher, where would be the TRPTC, and here, membrane, and specifically within what is membrane, it would be an ionic channel. Then we have ionic channels, we have receptors, and here receptors of various types. And here only 3 are shown, but there are many types of receptors. And for example, one of the most abundant receptors, the receptor coupled to G protein or GPCR, is good. There are receptors with less or more domains of transmembranes there. There are receptors that have enzymatic activity. The ligand inside a biochemical reaction occurs now at the level of the cytosol. We have the enzymes, and within the nucleus, there are also receptors called nuclear receptors, or in the case of antitumorals, the same ADN can be our target when we want to block its cell replication. So, there are the great receptors that we are going to be studying. Well, when we talk about optimizing a prototype, we refer to improving a structure, family of structures from certain rational modifications. This that we have here is a star or a relationship structure activity around a nucleus of interest. This nucleus of what would it be already very good, excellent. They are already identifying molecules, that is, it is a perfect antibiotic. Then we are going to see this and how the salt is done and what are the salt criteria to modify a prototype. You will modify a prototype to optimize what? Good thing, for example, modify the biological activity, that is, the dynamic drug. We want to modify the power. We want to make the drug more selective, or we want to do it multi-target in some cases we want the opposite eye with that, or reduce its toxicity. Example, in the case of some compounds that act at heart level is given as a punctual example is that of the digital. This molecule is the digoxin that increases heart contractility. But if we go over the dose, it can generate a stop. Sometimes you want to modify your pharmacokinetics, or you want to take advantage of the pharmacokinetics. You want to improve absorption distribution in the metabolism or the excretion of said pharmacist. Oh yes, if it is synthesized but in personal. I think it is cheaper to extract it from the plant because it is more or less complete. In fact, if you look at it, we have this part here that is exact, and this is what is. Technically speaking, this is a steroid type derivative. It is a steroid. It is a peridrophenanthine cyclopentane that is connected by the upper part as these systems of Any functional group is this one that is here, a cyclical ester. And that is one. A lactone, very well now. If I asked you, that is a point of relevant metabolic degradation. Of course. Yes, because very well. Because the esters are hydrolyzable by sterases. So yes, that is a point of relevant metabolic degradation. And of course, the lifetime there is not true. It is reduced when there are several metabolic points, okay. And we have a terminal part of semi-carbohydrate type, we could call it, which is the portion there where these three rings of interconnected cyclohexanide type are already. Then it would be the famous digoxin that is extracted from, I think it is called, it has a name, Digital is the cream is called that plant. And here we have, now that we want to modify pharmacokinetics, or sometimes knowing the pharmacokinetics, we create something new. Look. How interesting. I can ask you a question when one wants to create a drug of this type already with this chemical structure first. What is that short-term memory? We saw them a little while ago. And look, 1, 2, 3, 4, 5, 6, 7, then 7. Very well, a benzo, because here next to it, there is a benzeno exact. Yes, benzodiaz comes that there are 2 nitrogens and epine, because it has 7 benzodiazepine. Then the diazo is that there are nitrogens and the epine is because it has 7 atoms in total. That is a psychotropic. Then psychotropic. This is an agonist of the brain, GABAergic channel that is hyperpolar cells and produces relaxation and good. That is what is now conceptual question. That for a psychotropic to have activity here, you can have anything. But in position 2, that we are seeing there, well, this continues here. It is not true. We have to have a carbonyl or something similar to a carbonyl. That is a so or something similar, and day. The system continues there. That is, it is an indispensable requirement for interaction with the GABAergic channel that there is an accepting function of the hydrogen bridge as a carbonyl. The most occupied is a carbonyl. That is, if there is a carbonyl, how is that? With a carbonyl, it is going to be called, it is not amine. And as it is a cyclic amine, a lactamac. That is different from lactone, and they are different things. And then ask if it is so important that there is a carbonyl there because that one does not have it. It is called meditapam, and it is sold, it is administered as psychotropic. But I do not know if the carbonyl is so important, because that one does not take it then. As a senseless one, some explanation is going to have a terrible activity. What happens is that that carbonyl is super relevant, and as I tell you in general, an accepting function of the hydrogen bridge here is not always carbonyl, but one of the most used carbonyl then that there should be a too high dose. It is not very convenient. There is another reason, and it turns out that this meditapam, I think it is called meditapam, to see if meditapam is commercially available, and super high average lifetime. It has a high average lifetime. That is, it takes a long time to degrade. It lasts inside the body. Average lifetime is the time in which half of the organism's drug is excreted, many times by urinary tract, then some that acts for another mechanism, and the truth is that the reason is not so complicated when this is ingested by oral vein. you know that everything that one swallow goes first to the liver, passes through there and in the liver. Exactly in the liver, an oxidation occurs right there in that position. The liver inserts the carbonyl by oxidation, so it is a propharmacist in reality. And we are going to place propharmacists. So, at the hepatic level, the metabolism occurs. Sometimes we also want to modify the OI structure to improve the formulation, the stability of the molecule, the solubility. We can form salts to improve its stability or to improve its solubility. Application question. Here below is the clozapine molecule. When you see this type of structure, you also, that is a tricyclic system that has a nitrogen chain connected. This is an antagonist of brain dopaminergic receptors, and therefore it is an antipsychotic. The truth is that all these mental disorders are complex situations and sometimes multifactorial, and try to encapsulate what happens in the mind of a person only. Nothing like that is a super simplistic matter of the understanding of the whole brain. But at least this molecule, what it does in some way is to stop, for example, some behaviors such as hyperaggressiveness. Okay, well, the clozapine sometimes must be injected because the schizophrenic patient sometimes does not collaborate. He does not want to take the antipsychotic. But if you want to make an intravenous injectable, for example, something fast, you cannot inject that directly. A thrombus will form there in the blood. The area of T. Injection will be inflamed because it is injecting a solid dispersed in water. This is water. This is super lipophilic. How would a salt do in which in the carbonyl? To see how this heterocyclic was called, because it is forgotten already perfect, very well. And then, here where the methyl is already perfect, if there we can form a salt, for example, we can form a clear type of salt, a chloride, so that we have a chlorine as against a chlorhydride formation by bubble. We would have the protonation of this system, that nitro-basic this later would follow this here. This system, okay, and in particular, which of the two would be the one that would have some probability of protonation of these two that are down here, which of the two, if it was protonated twice, which of the two would be the protonable? And very well, because the one below exactly, very well, then, the one below is the charge concentration. So if it were to protonate twice, I do not know the value of this system, because if it is no longer an atom, they are two interconnected atoms. So pK is going to be altered due to that. And we would have to see what case it would be this. But this one here, for no reason, because this is exact. It is too much conjugated by resonance to both sides of the aromatic rings. Well, the other reason to form a salt, because it has to do with that. The formation of a salt increases the chemical stability. A salt will always increase the chemical stability. Read the boxes of their pharma. With the challenges, they are always like salts. If one buys, I do not know any of these for example, the chlorphenamine says chlorphenamine, that it is for the colds, chlorhydrates or mediates a certain form of salt. Some salt, because in that way it is more. It is degraded, less by oxygen. Light is a drier solid, harder, all that well. What happens when by modifying, we do not find analogues of great activity? It does not matter. The construction of an equation is advanced user question. How many molecules do we need to build an equation already very well over 10? That is against the best. We had said that 10 as the limit has to be greater than 10 more better, because we have a r squared, more fine, more exact. If we do not find activity, it does not matter. We advance in understanding the pharmacophore, which is one of the main objectives of medical chemistry. And before defining pharmacophores in a technical way with quiz, you will remember that we had said that the IC50, we have to transform it to perfect very well to PC50. And here arises another question. When one graphs at the PC50, and how many units should cover, because I am going to have PC50, for example, 4.1, 4.3, 4.05, etc. How many units of PC50 for the Kusar equation to make sense? Well, it has to be ideally from 2 up. Between the least active and the most active, there must be 2 or more logarithmic units of all difference. If you have less, the line is short, and therefore the regression is bad. And here is the question: how do we define the pharmacophore? Answer: by the structural path. That is to define a common nucleus. Or by the geometric path, that is to define elements in common. When I say elements, I do not mean chemical elements. The geometric path defines certain elements, such as hydrophobic groups, and also distances. And this way is the best. It is the most exact, but it is the most complicated to find. Then structural pharmacophores, example, that some of them again have to know this clear and into. In fact, some of these, they are going to identify it quickly. Look, for example, we go to those who have already, because it is antibacterial, because it imitates what it imitates. To be careful. Very well. The power exactly perfect. This imitates the power. And they are identifying some things, some more additional. Second example, when we saw the case of cocaine and the cocaine, for example, we already saw this aromatic ring had an aromatic ring of this type. Had here an amino, and then in the part that follows here, the cocaine had an S. Then it had an aromatic ring, a connector Z, where Z is, for example, an ester, which would be all here then. It had an N of 2 specifically, and then a protonable nitrogen that had 2 acyl chains. That was the example of the protein that was a local anesthetic. Third example, since there are several, but I am going to mention, because you should know this, because this one that looks quite simple, that is like Benson with a chain. This came from a very complicated molecule, an aromatic ring, a quaternary carbon. That is, this carbon that is here is not any carbon, is a quaternary carbon. A carbon without hydrogen. Connected to it only are chains, and from that same carbon, there are 3 atoms, not 2. There are 3 to this basic protonable third-type nitrogen. Well, I do not know. I am going to name some that is similar to what we saw recently: codeine, heroin, morphine. Now, if we are narcotics, and they are narcotics agents, and they all have this hidden pharmacophore. No matter how complicated the structure is. How was morphine when morphine had a ring of 5? And what else did we have here? We had the aromatic system with what thing with a phenol? Then we had that for the other side. There was also a ring, but connected with a double link, and we had to here. It came out if we raised this a little. This system came out like this, and here we would have 1, 2, 3. This was a system that goes up and ends like this. 1, 1, 2, 3, and nitrogen. 1, 2, 3. And then a nitrogen atom that had a methyl group. And then we would have to see 1, 2, 3, 4, 5. And here we had a GH2 nitrogen, then that was the morphine molecule. And there I was missing. Something I was missing here, I had another. It was like that. And then the morphine that we have here has this pharmacophore. No matter how complicated the structure is, note where is the water, carb. Very well. Exactly. There is, as it is, and if we count, we also have the 3 and then 1. I have to mark in red. It would be 1 later to see where it would be 2, 3. It actually gives the same 1, 2, 3, and up 1, also clear 1, 2, 3. And the nitrogen, then there is 1, 2, 3 nitrogen. 1, 2, 3 nitrogen. Protonable nitrogen. Of course. Yes then. As complicated as this simple pharmacophore of narcotics, so your mission now is to train in what? Sense in which, here are the pharmacophores. What I am going to ask you, pharmacists, names for these pharmacophores that are being given here. It will not direct to find some particular pharmacist, but for example, I am going to give you a pure, you are looking for this on the internet or in a medical chemistry book, such as Patrick's Medical Chemistry. That is a book that I recommend. That is the author Patrick Medicinal. Chemistry Patrick there. You will find, for example, tricyclic antidepressants there. You can look for things such as amitriptyline. What more antihistaminics there? You can look for example, chlorphenamine, etc. And I want you to, from there, when you see those structures that are going to be more complicated structures, notice that there are these patterns that are being given here, okay. Then knowing these patterns, you say, but tomorrow I do not want to create a new, and knowing these patterns when you see a new molecule, you will be able to predict if eventually some of these effects could have this molecule. So my goal is that seeing some structures predict biological activity to the question. And this here, because it is the let's have a second in this to finish. And so here we could talk for hours and hours about all the chemical structures. But why is this a moral anti-tumor of that structure so simple here in you can take various things, small cycles of benzene. Or what do I pharmacokinetics, any idea? Could already be a bridge of halogen. In fact, the bridge, there is a super important question that has to do with that. The bridge of halogen is better when the halogen is connected more than a chain to an aromatic ring. And in fact, this has been seen that when one wants that the bridge of halogen occurs when the halogen is in a chain, there are molecules that have this functional group. Put yourself here to see in the vicinity. Here it has, for example, a trifluoromethane, a CF3. The CF3 can be a bridge of halogen, not because they are flu, but a group is placed. A CF3, or similar, in the vicinity of the halogen, with what purpose? what perfect thing. Then it is an electro-attractor, and what happens? Benefit to the chlorine, in which it is exact. It is polarized more strong. That is, we generate the sigma, whole of course, that is exactly the sigma. And there are drugs that have, I do not remember that I recently saw one, but they have in the vicinity structures of type trifluoromethane or difluoromethane, with the film group to rare good. The purpose is, as the halogen did not remain a chain whole, because the bridge of halogen is better when the chlorine is a carbon of an alkylic chain, and why? And there again we would have to ask the question, why the bridge of halogen is better if this is connected to a carbon sp2 than a carbon sp3. Out there it goes that we refine the answer. And of course the carbon sp will have the C double. But in what benefit that question? More than that, the carbon sp2 has greater or less electronegativity than the carbon sp3, which is more electronegative. Well, carbon sp2 is more electronegative than carbon sp3, and being more electronegative, it polarizes more chlorine than a carbon sp3, increases the sigma whole, then, i.e., on that. But we have not yet given the answer. And with the anti-tumor, there you say mustard and other than nothing in condiments and things like that, and exact mustard gases, that is toxic substances and war gases in fact. Because this is an anti-tumor, how can it damage the tumoral cell? Well, this and the answer is not so trivial to see. I am going to erase this experiment within the cell. The following. Change the nitrogen entropically is very favored to attack. Who? Because the nitrogen is a nucleophile, who is the electrophilic, the carbon dialluro of the kilo OK. This is from the tamas here and here. It is also from the tamas. Therefore, we can have the nucleophilic attack in this way. And when that happens, what is going to happen to erase there? To stay with nitrogen, and it is going to form an acid and an acididonium, and this is going to be like this. And we have that this is going to stay here as a positive charge, and the question is this: what is a nucleophile or a strong electrophilic? A strong electrophilic, and the DNA is full of nucleophilic atoms. Then, for example, or the nitrogen bases, directly some of them could attack which position? We have two positions, could for example attack here. Okay, and this. The stem rents the genetic material is a rent agent, and therefore it alters the nitrogen bases, producing mutations, preventing the DNA from being able